Hello everyone, so let me introduce you to our group members. So, first of all, we have Stephanie, who is our group leader. Next, we have Dayang Zulaika. Then, we have Claudia and Janita. So, these are the contents of this video. In this video, we are going to explain the application of differentiation in our daily life, state the problem, solve the problem, and making conclusion.
Hello, my name is Dayang Zulaika. I'll be giving a little introduction to the application of differentiation. Differentiation is a fundamental concept in calculus. It has a wide range of real-life applications in different fields. It is particularly useful in analyzing and optimizing various processes, providing valuable insights and solutions. Let's explore some key applications of differentiation in real-life scenarios. In physics and engineering, differentiation helps us understand motion and change. We can obtain velocity and acceleration by differentiating displacement with respect to time. This knowledge is crucial in designing vehicles, predicting the behavior of moving objects, and developing control systems for robotics. Meanwhile, in economics, differentiation is useful in maximizing profit and minimizing cost. By differentiating cost and revenue functions, we can determine the production level that maximizes profit. Additionally, the concept of marginal analysis, which involves calculating the rate of change of cost or revenue, helps in optimizing decision-making processes. This also applies in medicine. Differentiation plays a vital role in modeling physiological processes. By differentiating functions that describe the growth or decline of substances in the body, such as drug concentrations, we can analyze the rate of change and make informed decisions about dosage and treatment strategies. In the field of computer science and data analysis, differentiation is used in machine learning algorithms and optimization techniques. It allows us to update the parameters of models based on the gradients of objective functions, leading to improved predictions and learning processes. We have also been learning how and when to use differentiation in calculus. One of them is when determining rates of change. Related rates problems are usually a relationship between two quantities of different variables. For example, a situation of finding the rate of change in the size of an expanding object with respect to time. Secondly, when doing analysis of functions. In here, we are understanding the behavior of a given function and identifying possible relationships and assumptions. Example, studying the details of a graph, including its domain and range, continuity, differentiability, extrema, concavity, and asymptotes. Finally is when we are finding maximum or minimum values of functions. Applied maximum and minimum issues give chances to optimize resources, maximize earnings, minimize expenses, optimize designs, or identify optimal solutions in a variety of practical scenarios in order to make the most optimal decisions. For example, finding the maximum amount of water for a swimming pool.
For the problem statement, a piece of wire of length 10 meter is cut into two pieces, one of length x meter and other is 10 minus x meter. A piece of wire with the length x meter is bent to form a circle, while the other piece is bent to form a square. For the question of this statement, find the minimum area enclosed by these two pieces of wire. First step, let's find the area for the circle wire. Since the x meter is equal to the circle circumference, which is c equals to 2 pi r. Rearrange the formula in terms of x and pi. So, the r is equal to x over 2 pi. Then, in the formula of the area of the circle, which is equal to pi r squared, substitute r into the formula. The area of the circle wire is now x squared over 4 pi. Next, find the area for the square wire. The perimeter of a square is equal to 4 times length of one side, which is 4s. Rearrange the formula in terms of x. Then, substitute s into the area of the square formula. The area of square wire is 10 minus x squared over 16. The total area enclosed by these two pieces of wire is the sum of the area of the circle and the square, which is x squared over 4 pi plus 10 minus x squared over 16. In order to find the value of x, the first derivative test is used on the area function. Differentiate the area with respect to x. Let dv over dx is equal to 0 and we will get 2x over 4 pi minus 20 over 16 plus 2x over 16 equals to 0. Simplify it and we will get x equal to 4.399 meter. To test the area whether it is minimum or maximum, a second differentiation is applied. Differentiate it again and the final answer will be 0.0341. Therefore, the area is minimum because the value is greater than 0. Lastly, to find the minimum area enclosed by these two pieces of wire, substitute x equals to 4.399 into the total area. Simplify it and the answer will be 3.5 meters square. So, the minimum area enclosed by these two pieces of wire is 3.5 meters square.
So briefly, the problem statement from the question is, what is the minimum area enclosed by these two wires? Therefore, after we found out the total area of circle and square, we can use the first derivative differentiation and second derivative differentiation to test the area is minimum or maximum. To sum up, we have used 4 types of formula that are the area of circle, area of square, the sum of area of circle and square, and the technique of first and second derivative differentiation. Next, the minimum area was proven by using the second derivative differentiation, and how an area can affect the change of derivative differentiation. Therefore, for a maximum would not be this possible if the wire is cut into square or circle as small as possible or as large as possible. So I would say that for a maximum, the wire should not be cut at all. Lastly, the concavity of wire can be determined by using the technique of derivative differentiation.